So the next two talks we switch to English. Our next lecturer is Steve Scott. Steve Scott is the Chief Technology Officer for NVIDIA Tesla Business Unit, where he is responsible for the Tesla roadmap and architecture. Before joining NVIDIA in 2011, Steve served 19 years at Cray. He holds 25 US patents and received the 2005 ACM Morris Wills Award and the 2005 IEEE Seymour Cray Computer Engineering Award. He received his PhD in computer architecture in 1992 from the University of Wisconsin, I guess, in Madison.
Thank you. I apologize for my Hebrew not being so good, so hopefully English will be okay. As you just heard, I spent the last about 20 years or so at Cray, where I was part of the team that built the first computer to sustain a teraflop on a real application, and then later part of the team that built the first computer to sustain a petaflop on a real application. And now, of course, we're all chasing a sustained exaflop, hopefully by the end of this decade. So there are good reasons to try to get to exaflop level of computing. There are problems that can be solved only with an exaflop computer. In order to simulate a global Earth model at a fine enough resolution to capture ocean eddies and cloud convection, you actually need a 1 kilometer grid, and with a multidisciplinary application, you need an exaflop of performance to do that. To simulate an internal combustion engine with full fidelity using large eddy simulation actually requires an exaflop of computation. To do a whole cell simulation at the molecular level all the way up to the biological level coupled together to allow us to understand disease agents and how cells work, scientists believe they need an exaflop computer. And to deny or confirm basic theories about supernovae and the formation of matter in the universe, again, an exaflop of computers is required. Once we get there, then everyone will start talking about zettaflop. But for now, it's exaflop. And if we take a look at the progress that's been made to date, we would believe that an exaflop computer is just around the corner. We should get there by 2019. I think we've all seen this chart. Probably half the people in this room have presented this chart from the top 500. And the middle line there is the number one machine. And if we extrapolate that, indeed, we should be able to get to an exaflop computer by 2019. But the problem, of course, and Daddy talked about that earlier today, is this number one machine over time has been getting much larger, it's been getting more expensive, and it's been getting more power hungry. In fact, if we compare the number one machine back in 1993 when this list was started, it was a Thinking Machines Connection Machine 5. It was only about 200 kilowatts. And now the number one machine is around 10 megawatts. So it's increased not only in cost and in size, but in power by a factor of 50. And we can't keep doing this. We can't keep building larger and larger and more power-consuming machines. But it's actually much worse. And that is because the underlying silicon technology has been cooperating with us for many, many years, decades, and that's changing. So we've had several decades of what's called constant field scaling, or Dennard scaling, where every time we have the transistor size, we've gone to a transistor that's half as long, we've also dropped the voltage by a factor of 2. And that means that the cost of switching a particular transistor has gone down by a factor of 8. The frequency has doubled of the transistor. The density has quadrupled. And all this time, the power has stayed constant. And this has taken us all the way from a megaflop to a gigaflop to a teraflop and most of the way to a petaflop. We've had this wonderful exponential improvement in performance at constant power. Corresponds actually to about 68% a year improvement compounded annually in the underlying silicon technology. It's been great. Now, during this time, the transistors have been giving us 68% a year. Our processors have gotten faster by about 50% a year in terms of the performance per watt over the past few decades. Some of that underlying technology, we spent that on building better and better single-thread performance. So we built more complex processors with deeper pipelines and more speculative execution. So we haven't translated all of that underlying technology improvement into performance. But we've done pretty well. Unfortunately, at this point, leakage current is getting to the point where we can't continue to drop the voltage. We're getting close to threshold voltage. And going forward, the new reality is that roughly if we have the feature size of a transistor, we only get about 2x the capability for the same performance. So that corresponds to only 19% a year. So we're under a dramatically tighter constraints and lower rate of improvement going forward than we have enjoyed for several decades. And the result is we have now become power constrained. It's really hard to overstate the importance of this. Right now, if we took all the transistors we could fit on a chip and we ran them as fast as we can, the chip would generate so much heat it would literally burn up. So we are constrained not by transistor density. Moore's law is alive and well. We're constrained by power. And it's going to become worse. With every successive generation, the density is continuing to increase quadratically until we get down into the quantum range and Moore's law truly ends. But the energy per operation is now only decreasing linearly with feature size. And so we're power constrained today. We're going to be more power constrained in the next IC generation and more yet. So high-performance computing has become entirely about energy efficiency. And it turns out that compute is not the only thing that takes energy. Moving data also takes energy. Now, sometimes we lose sight of exactly what a flop is. We talk about a megaflop or a teraflop or an exaflop. An exaflop is 10 to the 18, 1 followed by 18 zeros, flops. So this is a flop on the left. This is actually 2 flops, a multiply and add. And if we take the amount of energy it takes to perform that and compare it to the amount of energy that it would just take to move the operands, 18 millimeters across a die, turns out that it takes over 4 times the energy in 40 nanometer technology to move operands across the die than it does to perform that complicated operation. And that's going to become worse. By the time we get to 10 nanometers at the end of the decade, it'll be 15 times more energy. So moving the data is the really expensive part. And heaven forbid if we actually have to move that data from off of the chip hundreds of times. More energy to move the data than to do the computation. So, So, flops are cheap and communication is expensive. Now, if we look forward in time, if we want to improve our energy efficiency, there are really only 2 things we can do. We can reduce overhead and we can minimize data motion, try to exploit locality. Well, if we look at what the industry at large has done about power efficiency, we've moved to multi-core CPUs. So instead of having one CPU, one core on a chip, and trying to make it as fast as possible and build ever more deeper pipelines and more complex processors, we get our performance through parallelism. We back off on the clock frequency. We put multiple CPU cores onto a chip and better exploit locality. And this has worked pretty well. But the problem, when we really try to optimize for power efficiency, the underlying problem is that the CPUs themselves are not designed at their core for power efficiency. They're designed brilliantly, very, very well, but they're designed to make single threads run as fast as possible. They tend to use fast clock rates with deep pipelines. They try to deliver data to a processor as quickly as possible. With large caches that tend to be power hungry. They try to issue multiple instructions every clock and then dynamically figure out, can I issue these 2 instructions at the same time, or does this instruction depend upon the result produced by that instruction, so I have to serialize them. We try to work speculatively. Well, here's a branch instruction. I'm not really sure which way it's going to go, but I think it's going to go this way, so I'm going to start executing that work, and later on I'll figure out, did the branch really go that way? Oh, no, it went that way. I'll unwind and I'll start executing the other path. And so there's a lot of overhead. And it turns out that if you take a look at... Why does it keep doing that? If you take a look at a modern high-performance CPU architecture, the actual power that goes to the arithmetic logic units that are doing the adds and multiplies and shifts is about 2% of the total power. And the other 90% is in data movement and orchestration, trying to schedule instructions and make that thread run as fast as possible. So there's a lot of overhead. And if we take a look at 2 processors that were designed about the same time in similar technologies, we can really see the difference. If we look at the Westmere processor in 32 nanometers and the Fermi GPU processor in 40 nanometers, and then just look at the peak flops and the peak power of the chip, we see about a factor of 7 difference in terms of the amount of energy. It takes about 7 times more energy, higher overhead, to do each flop in a CPU than a GPU. But this does not mean that the CPU is poorly designed. That CPU is brilliantly designed. It is very, very well designed, but it's optimized simply for a different target. It's optimized for single-thread performance. A CPU has about 8 cores on it. A GPU today has 512 cores. Each one is very small, very simple, and it's because the GPU was designed for graphics workloads before computing. GPUs were designed to run hundreds and hundreds of threads at the same time and optimized for throughput and efficiency, not for single-thread performance. The single-thread performance of a GPU core is not very good. So if we have to reduce overhead over time, if we're becoming more and more power constrained, the question is, can we just take the CPU design and make it more energy efficient, try to reduce that overhead so a greater fraction of our power is going to do the actual operations in the ALUs. And the problem is that you really can't do that and still be a good CPU. And a recent example is illustrative. If we take a look at the new AMD processor, the Bulldozer core that just recently came out, and compare it to a Xeon core, the Bulldozer core is a little bit more energy efficient. There are more of them on a die, but the single-thread performance is not as good as Xeon. And as a result, the market reaction to Bulldozer has been very, very negative. Doesn't get the same single-core performance that you can get in an Intel Xeon core. And AMD is getting hammered about this. And this is just backing off a little bit, trying to be a little bit more energy efficient, but losing on single-thread performance. So the problem is if you got rid of all the overhead in a CPU core and made it as energy efficient as a GPU core, it would no longer be a good CPU. So the conclusion that I've come to, and the reason that I got so excited about GPU technology and NVIDIA and decided to come join the company, is that the future has to be heterogeneous. We have to do most of our parallel work on cores that were designed first and foremost for energy efficiency, and then the leftover serial work, we need a good CPU, a fast CPU, to execute that. And the market seems to have come to the same conclusion. We've seen pretty widespread adoption of GPU computing over the past few years. There are now millions and millions, hundreds of millions of compute-capable GPUs out there that people can use, and there have been over 1 million downloads so far of the software development kit from NVIDIA. We think that there are currently about 100,000, a little more than 100,000 active developers using GPU computing. And 5 years ago, there were effectively 0. And there are now almost 500 different universities that are teaching parallel computing using GPUs, and almost all of the major OEMs have adopted GPUs as part of their lineup. But it's really been at the high end that there's been the most remarkable adoption. It was just 3 years ago, last month, that the very first GPU-accelerated computer showed up on the top 500 list. 3.5 years ago, there were exactly 0 GPUs on the top 500 list. We've now seen a tripling of the number of GPU-enabled computers in the last year. They've doubled since last June. And if we look at the very high end of the top 5 systems on the top 500 list today, 3 of them today are GPU accelerated. The Tianhe system in China, the Nebula system in China, and the Tsubame system in Tokyo. And the number 3 machine today, the Jaguar machine at Oak Ridge National Laboratories, is right in the middle of being upgraded now to GPUs. Oak Ridge has announced that they're changing it to a new machine called Titan, which will have 18,000 GPUs in it, over 20 petaflops. I'm particularly excited about this because in my former position at Cray, I've worked with Oak Ridge for the past 10 years or so, and we've done multiple generations of machines, starting from just over 2 teraflops in the first machine at Oak Ridge, now to over 2 petaflops. So about a factor of 1,000 over the last decade at Oak Ridge. And when we sat down to try to figure out what were we going to do next, what was the machine after Jaguar, we came to the conclusion that we couldn't get there because of this looming power constraint. We could no longer get there with another generation of CPUs. We had to use GPUs to get there. So when Titan gets installed next year, it'll be over twice as fast and over 3 times as energy efficient as the current number 1 machine, and much, much smaller. It will be in exactly the same footprint as their current machine today. And this was a pretty big endorsement of GPU computing. Oak Ridge is the world's premier open science computing facility. They are responsible for some pretty important problems in energy, in climate research, in transportation, and for them to say we're going to go all in, we're going to build our next machine entirely accelerated by GPUs is a very gratifying endorsement. I'm pretty proud of that. But GPUs would not be being adopted if it weren't for an increasing ease of programming. This is actually the area that I think I'm personally trying to focus us on the most at NVIDIA currently. CUDA was just introduced 5 years ago. This is a way of programming GPUs in a high-level language. And CUDA has been quite successful, but CUDA is limited to people that are really computer scientists, that are willing to roll up their sleeves and do some detailed programming. And in order to have much broader adoption, to be used not only by computer scientists, but by regular scientists, biologists, chemists, physicists, etc., we really need to make GPU computing even easier. So now there are really two ways of using GPUs that do not require programming in CUDA. The first is simply using GPU-accelerated libraries. If you're doing fast Fourier transforms in your code, you don't need to know you're using GPUs. You just call the GPU-accelerated FFT library and get very good results. If you're doing dense linear algebra or sparse linear algebra, there are hundreds and hundreds of different routines now that are available using libraries. There are domain-specific libraries like CUDA, which is for quantum chromodynamics. There are the thrust set of parallel libraries, which are basically templated C++ libraries for doing sorting and searching and other sorts of algorithms. So it's become much easier to just use libraries that are GPU accelerated. But what I'm particularly excited about is using directives. Directives are a way of programming GPUs without having to do platform-specific optimization. You could take your original C or Fortran or C++ code and identify regions that are to be parallelized on the GPU with directives that you insert into your code, and then the compiler does all the low-level work of mapping that onto the GPU, handling any data movement, synchronization, etc. And this really leads to a specialization of labor where the human focuses on exposing parallelism, which compilers are not good at because it requires whole program analysis, and it's often very difficult for a compiler to know, is it really safe to parallelize this code? Because maybe there are some pointer dereferences that would cause dependencies that the compiler can't figure out. But the user, the programmer, can, if they know that this is indeed parallel work, they tell the compiler that, and then the compiler can take care of mapping the code. And then all of the low-level details the compilers are very good at. And it also results in portable code, code that can run on GPUs, code that can run on multi-core CPUs. So there are a few companies that have started developing directive-based compilers for GPUs. One of them is PGI, Portland Group, and one of them is one of them is CAPS in France. And we started to have over the past couple of years a large number of users that are working with accelerators, using directives, but they had different standards. And we got a lot of feedback from them saying we'd really like to have a single standard for directives for accelerators. And so we got together with PGI and with CAPS and with Cray, who is also developing a directive-based compiler, and came up with an open standard called OpenACC, a common set of directives that will be implemented in the CAPS compiler and the PGI compiler and the Cray compiler. And OpenACC will be available starting next quarter and will be usable for both programming GPUs and for programming multi-core CPUs. The folks at Oak Ridge are very excited about this because it's important to them when they have large community codes that may be 1 million lines of code. They really want to have a single code base and not have to have one code version for their CPUs and another version for GPUs that's written in CUDA. So OpenACC allows them to have a single set of directives, easily port their codes, and then run them everywhere from a Blue Gene to a power system to a standard x86 cluster to a GPU accelerated cluster. We're also working to move this into the OpenMP standard. Michael Wong, the CEO of OpenMP, is very enthusiastic about OpenACC, and we anticipate that the next version of OpenMP will incorporate that standard. But the really exciting thing about this, to me, is that the user spends their time when they use directives not doing platform-specific tuning, but rather exposing parallelism in the code. You're really making the code inherently better by trying to expose more parallelism and not spending your time trying to deal with the intricacies of a specific algorithm. And this can be seen by a couple of the codes that are being developed currently for the new Titan machine at Oak Ridge National Lab. S3D and CAM-SE are two of their flagship applications. And S3D is a combustion code. They took the top 3 kernels of this application and tuned them using directives. They had to do some work to expose more parallelism in the application to get good performance on the GPUs. But when they did that work, they found that the same code now ran substantially faster on the CPU-only system. So these 3 kernels ran anywhere from 3 to 6 times faster, comparing one node, which had a CPU plus a GPU, versus another node that had 2 CPU sockets, so equal number of sockets. So 3 to 6 times faster, but the same code was also 50% faster on the CPU-only version. The same thing happened with CAM-SE. The top kernel there corresponds to about 50% of the runtime. And when they used directives, OpenACC directives, to port it to the GPU, and then they tuned the code to get better parallelism, the performance of the CPU-only version running on Jaguar, an all-CPU system, actually doubled. And yet still they were able to get 6.5-time improvement on the then optimized code on the GPU node versus the CPU node. So this is an incredible value proposition for the programmers, because their time is focused on improving the application versus spending time to do something platform specific. So I'm pretty excited about GPU computing. Again, that's why I decided to come and join NVIDIA. And again, it's very hard to overstate the importance of this statement. We really are constrained by power. It's going to become more and more important as we move forward. And it's really difficult to optimize both for single-thread performance and for power efficiency. These two things are really at odds with each other. You cannot have a processor core that has competitive single-thread performance and is also competitive in terms of power efficiency. And so the result of that is that we absolutely must go to heterogeneous computing. I'm convinced of this, and I think the world at large is becoming convinced of this. We do need a few fast cores for doing the serial work, but most of our ops, the high 90% of our operations absolutely are going to have to be done by cores optimized for power efficiency. And by having 2 different types of cores, we're able to really focus on power efficiency and bringing out overhead for those cores. I'm convinced also that GPUs are the right path to get to this heterogeneous future, and it's really for 2 reasons. One is the technological reason about having cores optimized for power efficiency, but the other is really a business reason. We could not do what we do at NVIDIA if it were just for the HPC market. I've personally been involved with multiple projects, both at Cray and working with microprocessor companies, where a processor that was being designed for HPC, even with some government support, ended up being canceled because the HPC market simply isn't big enough. It has large demands in terms of the technology that it requires, but it's a small market, and so you can't afford to build a processor focused just on HPC. But GPUs have a day job. They have a very, very large 100 million unit a year sort of market for graphics, and we can actually take the same processor that's designed for high-performance graphics and use it for high-performance computing. And that large market is able to sustain the development. And so there's a business model that works that I found very attractive. So put the technology and the business together, and I think it's a very compelling solution going forward. And with that, thank you very much.